So we should be able to finish regeneration today. Last time we talked about the open feed water heater, and we talked about how you would divert some mass from after a high pressure turbine stage and take it down to feed the open feed water heater, such that the feed water that goes into the steam generator and to the boiler is a higher temperature, so that the heating that is accomplished is all done at a high temperature as possible in the steam generator or the boiler. Okay? We talked about what is the symbol Y. Y is a mass fraction, true? It's a mass fraction, so it's the mass flow rate that goes down to feed the open feed water heater divided by the mass flow rate that came through the first turbine stage. And so it may be 20%, 30%, something. So let's often it's less than 50%. Let's say Y is 25%. Well, if 25% of the flow that comes out of the first turbine goes down, what's the percent that goes on for reheat? 75. So 1 minus Y. 1 minus Y is a fraction. So often when you are new in solving these problems, get your pressures everywhere, then get the mass fractions or the mass flow rates. It's just the mass fraction is a ratio of the mass flow rates. And so this would be 1 minus Y going through the second turbine stage, 1 minus Y going through the condenser, 1 minus Y going from the condenser into the pump, and then 1 minus Y coming in to the open feed water heater, Y coming into the open feed water heater, and guess what comes out? 100%, 100%, and then you're back to 100% of what goes through the first turbine stage. So you get the mass fractions. Here's a clicker question for you. Describe the steam at state 1. Would the steam at state 1 be called A, subcooled liquid, B, saturated liquid, C, a two-phase liquid-vapor mixture, saturated vapor, D, or superheated vapor, E? What is the best description of the steam at state 1? Where is state 1? Right here. Right? And it's superheated vapor. That's typically what comes out. All right? It's good to come out superheated. All right, so let's switch over here to E. Here's another question. So, what is the condition of the state at 4? State 4, how would you describe typically? I mean, you could change some parameters and it could change a little bit, but what we've been doing is we've been talking about steam, and what do you expect state 4 to be? Subcooled liquid, saturated liquid, two-phase, saturated vapor, or superheated vapor? And we'll show the results. So a lot of people believe that it's two-phase, and that's right. You typically want it to be a very high quality, but you do want to dip into that dome for that state at 4. And let's answer this one. Let's talk about state 5. How would you describe state 5? Would that be subcooled liquid, saturated liquid, etc.? A, B, C, D, E, state 5. All right, let's go ahead and show the results. So, B, saturated liquid is correct. And now let's talk about one more or two more. State 7. State 7. What is that? Well, this is what's coming out of that open feed water heater. What is the typical condition of that state? Subcooled liquid, saturated liquid, two-phase, saturated vapor, or superheated vapor? State 7. Everybody in? We'll go ahead and stop then and show the results. Well, State 7 always a little more challenging than other states, but how can you tell that State 7 is a saturated liquid? It's got as much energy as you can get into it without giving that pump problems. And if you put more energy into it, it would go from saturated liquid to two-phase. We don't like that. Anything two-phase going into a pump. We want saturated liquids. Now, it can be subcooled liquid, but then that would have less enthalpy or lower value of energy content. And that's the whole purpose of this open feed water heater, is to get a lot of energy into the feed water. True? True? So that's true. Now, one more we'll play with. Condition at state 8. So after the pump, right before the steam generator, what is the description of the fluid, the steam, at state 8? And show the results. Okay, 8. Well, after the pump, and if you did feed the pump saturated liquid, think about a TS diagram. Straight up on a TS diagram, went into that little sliver of a narrow band of compressed liquid or subcooled liquid. So the correct answer is A. What's the difference between somebody says subcooled liquid versus compressed liquid? Compressed liquid. Same. It's the perspective. Either for a liquid, either the temperature is less than the saturation temperature. Doesn't that indicate that it's a liquid? Or the pressure is greater than the saturation pressure at that temperature. See? You'd say, okay, if you want to confirm that it's subcooled, knowing the pressure, get the saturation temperature at that pressure and compare the actual temperature with the saturation temperature. If it's colder, we would saw, oh, that's subcooled liquid. The other one is to say, take the temperature, get the pressure, the saturation pressure for that temperature of the steam or the liquid or the fluid, whatever it is, and then compare the actual pressure to the saturation pressure. If the actual pressure is greater than the saturation pressure, then you might call it compressed liquid instead of subcooled liquid. This is the perspective of pressure. This is the perspective of temperature. Right? Okay. We want to talk about getting that equation for Y. Well, what exactly was Y again? Y was that percent of the flow that came out of the first turbine stage that was diverted down to the open feed water heater, something like the mass flow rate down to the open feed water heater divided by the mass flow rate that came through the first turbine stage. How do we know what Y needs to be for optimal performance of this power plant? We don't want to send too much steam down there. We don't want Y to be too large. We don't want Y to be too small either. So how do we determine how much steam needs to be diverted? What is the magnitude of Y? What does it need to be? Well, the key is right here. What does the state 7 need to be? Saturated liquid. All right? So if state 7 needs to be saturated liquid, at what pressure is state 7? That's another thing. What is the pressure at state 7? Is the pressure at 7 equal to the pressure at 2 equal to the pressure at 6? Yep. Okay. So all that's what we would call the intermediate pressure. The high pressure is what came through the steam generator on the first pass. Like this is the high pressure right here. And the condenser pressure is our low pressure. But the rest of those are the intermediate pressure. Okay. So how do I determine the magnitude of Y? Get the equation for Y. Any guess? How would you get it?
the energy balance coming through the open feed water?
See, it's real easy to make me happy. You just started saying the right key words, right? Professor, I think we need to have a free body diagram. Oh, that makes your statics professor so happy. Right? And so you say, I think we need to do a control volume. I think we need to have a control volume around that open feed water heater, and then we're going to do an energy balance. We'll do a first law analysis for that control volume right here. Can we do that? Sure. Now we would write it like this. Maybe I need to manipulate a little bit, but how about the mass flow rate coming down to operate the open feed water heater? That's coming this way from state 2, bringing with it its enthalpy at state 2, plus what came out of the first pump and is bringing its enthalpy at state 6. But what really comes out of that first pump? Well, it's what went through the condenser. Okay, well, what went through the condenser? It's what went through the second turbine stage. Yeah, okay, well, that's what went through the reheat. Okay, well, that was the mass flow rate that came out of the first turbine minus the mass flow rate which was diverted down to the open feed water heater. Do you see how we backed up to get that mass flow rate coming through pump number 1? And all of that is going to go to be the enthalpy of 7 carrying out. But what's the mass flow rate of the fluid coming out at 7? Is it... Here, I'll ask a clicker question. Answer A. The mass flow rate coming out at 7 is the mass flow rate of the open feed water heater. B, the mass flow rate that goes through the first turbine stage. Or C, the mass flow rate first turbine stage minus mass flow rate open feed water heater. I will start and see what you think. So the mass flow rate going into the second pump. That's what I need. Are we going to get 100%? I think we'll get 100% on this one. And let's show it. Oh. Okay, well, I don't know. What we got is the fluid, okay, that then, this is the mass flow rate that's going to go into the second pump. That's the mass flow rate going up through 8 into the steam generator. That's the mass flow rate coming out of the first pass in the steam generator. That's the mass flow rate that goes through the first turbine stage. So it was m dot T1 times H7. Does that energy balance look complete? Professor, isn't there a lot of heat transfer in this heat exchanger known as open feed water heater? But it's internal to our control volume. That's why we, a lot of times, we're very careful. We say, this is our control volume, and nothing goes across that boundary of the control volume in the way of heat transfer to the surroundings. There's heat transfer inside the control volume, but not to the surroundings across. So what we do with this equation is we divide the whole equation by m dot T1, m dot T1, m dot T1, and then we recall, oh, you know, that ratio is y times H2. This is 1 minus y times H6. This is 1 times H7, true? And then you can rearrange to get the equation for y. Y, the amount needed to be diverted down to feed that open feed water heater such that it comes out saturated liquid, is going to be, in terms of the enthalpies, it's going to be H7 minus H6 divided by H2 minus H6. Did I do the algebra good? Thumbs up if you like it. Got a couple? Good. All right. So that's the equation. So in order to get the value of y, to say, oh, it's 18% or 22%, I need to know these values of h. Now you think about it for a minute. How about the value of H2? Well, it's what came out of that steam turbine through the first pass. If it's isentropic expansion, conceptually, sure. I'll get H1, then I'll get H2. All right. And then how about H6? How could I get that? Well, you're going to march around, you're going to come out saturated liquid at state 5, and then you're going to add the work of the pump, and you'll have H6. And then what about H7? That's saturated liquid. Did I say it enough? Am I emphasizing that point too much? Am I boring you? It's saturated liquid at that intermediate pressure. That's the design intent. That's what that helps the performance of the system, optimal. All right, let's press forward. So here's a problem, and you need to take these type of problems, you just need to work them. And I think I started talking about this problem last time. So I like to just stay with a certain high pressure. You know, I've been talking maybe a couple lectures now, 8 megapascal. Let's superheat it. How much? Let's just pick, so I just keep going 8 megapascal up to 440. Not a superheat, okay? And then we have to pick an intermediate pressure. I could expand to 2 megapascal. I expand to 1 megapascal through the first turbine stage. That's my intermediate pressure, 1 megapascal. And then if the stuff goes back for reheat, it gets back up to 440. It doesn't have to. In a power plant, you reheat to a certain different level, but reheat back up to 440, then go through the second turbine stage. And then the condenser pressure often is dictated by your cooling water. How cold is the lake that you're dropping it to? Or how about the outside ambient air? You have a big cooling tower. Okay, you're evaporating in a cooling tower. You don't have a lake. Or you have a bay, or you live, or they put the power plant right by an ocean or a big river. It's the temperature of the water, okay, that you can typically reject it to, or the temperature of the air that you can reject it to. And so I picked that it's going to have a temperature around 60 C, that's pretty warm, and it's around 20 kPa in that condenser. That's our low pressure. And then we go through and make a lot of calculations of all of these metrics, especially the overall thermal efficiency and the backwork ratio. Have we outlined, let's say what's the work, the first turbine stage? What is that? Have we done that enough? Energy balance shows that it's H1 minus H2. And I put it on a per kilogram basis. And so this is kilojoules per kilogram. Now, what about the work out of the second turbine stage? Well, that's H3 minus H4. Make sense? But when I talk about this kilojoule per kilogram, this is the kilogram that went through the second turbine stage. I'm kind of adding a subscript saying, that kilogram is what actually went through the second turbine stage. And then I go back and I say, this kilogram is what went through the first turbine stage. Are they the same? They are not the same. So what you can do, if you want to put all of these specific works on the same per unit mass basis, they often put them on the mass that went through the first turbine stage. So if I multiply this by a ratio of the mass that goes through the second turbine stage divided by the mass that goes through the first turbine stage, or if you like to think mass flow rates, put an m dot on both of them, then you'll see that the units convert over to kilojoules per kilogram that went through the first turbine stage. See the units? And then you say, but you know what? This ratio right here is 1 minus the fraction that was diverted. It's dimensionless. It's kilogram over kilogram, but it's a number less than 1. And so it's going to be H3 minus H4 times this 1 minus Y. And when a student sees that 1 minus Y, they shake their head. Why is that there? Because we want all the specific works and then all the specific heat transfers on the same per unit mass basis for the whole cycle, so we can just add them easily to get the net work and the net Q. Okay? So when you go down here for the Q going out the condenser, normally it would be just H4 minus H5. But if you want it per unit mass that went through the first turbine stage, multiplied by 1 minus Y. Now it'll be kilojoules per kilogram that goes through the first turbine stage. Okay? All right. What about, let's say, this pump let me do work of the pump 1. It'll be VDP. Okay, I think we understand that terminology, VDP. And it'll be 1 minus Y for pump 1. But when you go to pump 2, it'll just be the V coming in at state 7. It'll be P8 minus P7. That's the VDP. But there won't be any 1 minus Y because the mass fractions are back to 100% for the second pump. The mass flow rate through the second pump is the same as the mass flow rate through the first turbine stage. Makes sense? Very good. Once you have them all on the same per unit mass basis, then it's a lot easier to do the bookkeeping and combine them. Okay? Here is the solution. I encourage you to review this video and get these numbers and reproduce them. Now, I generated this with some software that you can download to your PC. It's off of the University of Alabama website. I have videos out on YouTube that shows you how to download it, although you probably don't need that video. You can probably just go there and figure it out. And then install it and put the add-in into your computer and run it.
I couldn't find it for Mac. Is there anything?
I doubt it's anything for Mac.
Okay.
It's some students every semester will say, well, I can run an emulator on my Macintosh.
Yeah.
But, you know, if they can, great. They have computer skills way above mine. So if you have a friend that knows how to do that, thumbs up. Or if you're good enough to do it. So, has anybody downloaded that software and played with it? One? Yeah, go ahead. I would encourage you to download it, okay? Okay. Once you've calculated a number of these things, you should be able to get the thermal efficiency of the cycle. It's around 39%. That's great. But we have no inefficiencies of the turbines or pumps or other things. It's going to degrade. And the backwork ratio, less than 0.7%, less than 1%, which is great. And then you can do this. Always, when you have a cycle and you're analyzing it, run and make sure that the work net equals the Q net. Double check. You know, as an engineer, a lot of times, or students, you know this, you say, well, I need to have the solutions to the problem. Because when I work it, I don't know if I made a mistake or not. That's true. Out there in the real world, you don't know if you made a mistake until sometimes it's built or something else happens. But anytime that you can get something to check your work, you want to latch on and use it to check your work. And in these problems, for this chapter and next chapter, go and compute work net, go and compute W net, Q net, and then they would be computed almost completely separate algorithms, right? It's like, what? How am I going to compute the Q net into the cycle? Well, it's going to be this in minus that out. So it's going to be the sum of those three players. What about the work out? I'm going to get this work out, this work out, this work in, and that work in. And you think, so some of those reds and the sum of those blues are going to equal? They better. Otherwise, you got a problem with your cycle. You have violated somewhere in the system the first law. So they need to sum up. Well, no. What happens in the field is energy is still conserved. It's just I have a bookkeeping challenge of keep getting it all. And there may be a pipe. And I insulate it to reduce the heat loss, but it's some heat loss in that pipe. And so... but energy is definitely conserved. It's just my bookkeeping becomes really challenging. Yeah. But in our cycles, this is a great check. Make sure and do that. Make sure and calculate Q net and W net and make sure they're the same. I do it all the time. Okay? Now let's talk about a different type of feed water heater. The first one we talked about was open. This one is a closed feed water heater. So what we have is the same idea of diverting some hot steam, and the hot steam doesn't mix with the cold feed water, but the cold feed water is heated up so that it doesn't go so cold into the steam generator, the boiler. So you have basically two ins and two outs. for a closed feed water heater. There is no direct contact between the two fluid streams. So the mass flow rate that comes from to feed the closed feed water heater is what comes out the bottom, mass flow rate that may be going down through what we call this steam trap. Steam trap. Okay? So what happens is, think about this. What type of, usually this is some intermediate pressure. Think of about 1 MPa pressure. That's a number I've been throwing around. And maybe some high quality. Maybe this is 98% quality, right? So what it does is it comes in here and it condenses on the outsides of tubes where the cooler fluid is flowing through the tubes. And when it condenses on the outside of the tubes, it collects in the bottom as a liquid. Okay? What pressure do you think that liquid is at the bottom in the shell side of that heat exchanger? Do you think it's at the 1 MPa? Or do you think it's at much higher pressure or much lower pressure? It came in as a high quality steam, and then it condenses and it's about ready to go out. So what about the pressure at state 8? Same pressure. You've got to work through the pressures. That helps. Get the pressures right, okay? So the pressure at 8, guess what? The pressure at 8 is equal to the pressure at 2. But now you've got a challenge. What am I going to do with this liquid? It gave up all its heat, so to speak. It transferred a lot of heat to that fluid going from 6 to 7 inside the tubes. It's now a liquid. It's a lot lower enthalpy. What am I going to do with it? Well, you got to feed it back into the cycle somewhere. You don't throw steam away. Okay, so here they're showing you it passes through a steam trap, a device that we'll talk about. Then it goes to state 9, and then it just dumps into the condenser. Before we talk more about the steam trap, tell me a little bit about the pressure at 4, the pressure at 5. Are they the same pressure? 4 and 5 have the same pressure? What pressure is it? 20 kPa? Low pressure, our condenser pressure. If I have an inlet from 9 going into the condenser, just a pipe feeding in liquid, what do you think the pressure is at state 9? 20 kPa. It's a low pressure. And now you've done it all. You've done all the work, okay? You've got the pressure here and you've got the pressure there. The pressure at 8 is 1 MPa. It's an intermediate pressure. The pressure at 9, 20 kPa, low pressure. What has to happen? This steam trap, what's it going to do? It's going to lower the pressure. It's a restriction. It's like a valve that's partially closed. That's what it is. So a lot of times when we have a valve, don't we have some symbol like this? Like a valve? And it's a pressure drop across it. There's a pressure drop across this. Now, this is a special type of valve. Okay? It's called a steam trap. They're very old. There's a lot of them out there in practice. And it's a good thing to know. But they're very simple in their goal. It's a police officer who directs traffic. And he says, red light, everybody stops and piles up. And when it piles up, guess what the liquid level does? Goes up. And then he says, oh, I got too big of a pile of liquid back there. Guess what he's going to do? Green light, everybody go. Come on, come on, come on, come on. But only liquid. No steam. I don't want any. I know that there's some vapor coming in here. And if I just said, let it all go, it could drain it. And then I could get steam going through. The vapor going through. And all I want is liquid. And so it's like a float system. You can see different schematics and designs of them. And it'll fill up with liquid. The float will go up. It says, oh, you're too full. It kicks the valve, flushes that liquid. But then the float falls, it shuts the valve. Make sense? And you can buy them, and they're designed. You don't need electricity to operate them. You don't need all these complicated things that can run day and night, hopefully for a long time. And but then they do malfunction every now and then. And sometimes when they malfunction, what do? They just stick open. When they stick open, unfortunately, it's a wasteful situation in a steam power plant. So a lot of engineers and maintenance guys go around and double check steam traps to make sure that they're functioning right. So steam trap is hopefully easy to understand, right? Okay, now what do you think? This is what's new now. Is there a pump on this fluid that's coming out at state 7? Is there a pump between it? Is there a pump anywhere in this system? Okay, tell me a little bit about the pressure at 7 compared to the pressure at 1. Is the pressure at 7 less than the pressure at 1, equal to the pressure at 1, or greater than the pressure at 1? The pressure at 7 is equal. All right, well, guess what this pressure at 1 was? A whopping 8 MPa or something. It's my highest pressure, right? So I just have this one pump. It's going to take it from the condenser pressure all the way to the boiler pressure, the 8 MPa. So pressure at 6 is equal to the pressure at 7 is equal to the pressure at 1. Okay? So make sure you get your pressures right. Now, what about, is it going to come out saturated liquid at 8 MPa? Well, before it came out saturated liquid, but that was because it was going into a pump to boost it from 1 MPa up. And if you came out before, if you remember, I kind of throw around some numbers. What's the saturation temperature at 8 MPa? Just a skosh under 300 degrees C, 295 degrees C. What's the saturation temperature of steam at 1 MPa? That's kind of our intermediate pressure we've used a lot, about 180 degrees C. And what's our saturation temperature at 20 kPa, the low pressure that's in this condenser? Around 60 degrees C. Got it? So, if you said, okay, we want this to be 8 MPa saturated liquid. Wow, it's going to be coming out 295 degrees C, right? All right. This steam that comes out here, maybe its quality at 2 is 95%. What is the temperature of the steam at 2? If the steam at 2 is quality of 95%, what is the temperature? And now I'm going to ask a clicker question. So, is it A, B, or C, or none of the above? I'll go ahead and start that. So what we want to know is we want to know the temperature at state 2. Is it this one, A? Is it this one, B? Is it this one, C? Or is it none of the above, D? The temperature at 2. Let's go ahead and shut it down. And then we show the answers. Show the answers. All right. So that temperature is right at the saturation temperature at the 1 MPa because that's the pressure at 2. And so it's around 180 degrees C. So I have steam coming in at 180 degrees C. What is the temperature going out at 8? What is the temperature going out at 8? Another clicker question. So we started. The temperature going out at 8, is it 295, about 180, or about 60, or none of the above? The temperature at 8. All right, I'll go ahead and stop. Then we'll show the results. All right, so the temperature at 8 is... Why is it 180 degrees? Because it's saturated liquid and it's the pressure at 2 is equal to pressure at 8. All you did was condense at constant pressure, right? When it condensed, all that HFG came out of the fluid, a lot of heat transfer, and it warmed up. So let me ask you this. If it's 100, the hot fluid comes in at 180, and the hot fluid leaves at 180, the cold fluid comes in probably around 60 degrees C, a little bit over. Remember, it's like a half a degree above 60 because it's coming out at 60 degrees C right here. All right, how am I going to have, even the most clever engineer, do you think I can design a heat exchanger that's going to bring out 295 degrees C? You can assume it, and if you did a second law analysis on it, guess what you would say about entropy? Entropy wouldn't be generated It would be destroyed in a heat exchanger like that. It would violate what law? Second law of thermodynamics. Okay? It's too good to be true. It can't happen. You're thinking, yeah, that's kind of not plausible, is it? That's really what second law statements are. It's like, no, that's not realistic. It's doing something that can't be done. So what do you think about the temperature of 7? What do you think? How hot could it come out on the best day? 180. And as a real engineer, knowing that you have some pick. So when you have a problem like this with a closed feed water heater, you read the problem and often they'll say something like, oh, and the temperature at 7 is given. They have to do something about it. They have to help you fix state 7. So they fix it. They tell you the temperature at state 7. And typically it's about 5 or 10 degrees less than the saturation temperature of the hot stream. So if it was 180 here, maybe it's 170 coming out there. It can't be more. It would be as high as it would be as the saturation temperature at state 2. Okay? All right. Sound good? Let's do one more thing. Let's get our equation for how much steam now is going to be diverted. Knowing, look at, if somebody says to you, if I tell you the temperature at 7 is 170 degrees C, could you get the enthalpy at state 7? Because we already talked about the pressure at 7 was the pressure at 1 is 8 MPa. Could you get the enthalpy at state 7 knowing that information? Yes, you could. So now the question is if I want to find out how much mass is diverted to feed the closed feed water heater, I have to do an energy balance around this control volume, around that closed feed water heater. And it'll look like this. I'm going to have Y times H2 minus H8. That's what's coming out of the hot stream, isn't it? Equal to, but I didn't do my mass fractions, but what is it? Is it going to be 1 minus Y here? Is it going to be Y here? Or 1 for what's coming through the pump, through this pump and in the cold side of the closed feed water heater? Okay, so we'll have this. I know it's going to be multiplying H7 minus H6, right? Now, it's either going to be 1 minus Y, or Y. So this is a great opportunity for answer A, answer B, answer C, or answer D, none. Make sense what I'm asking you? I'm writing an energy balance around there. It's either going to multiply H7 minus H6 is going to be 1 minus Y, or Y, or none of those.
Dr. McCorkle?
Yeah.
State 7, you said, is that a saturated liquid?
No. That's a great question. What is state 7? Maybe that's another question for your colleagues. Thank you. I'll ask it in a minute. How do you describe state 7? I won't do it with a clicker question. What is it, though? It's 8 MPa and at 170. The saturation temperature at 8 MPa is 295. The temperature is a lot lower than 295. Subcooled liquid or compressed liquid. All right, everybody in? Let's go ahead and stop and see where we're at. Well, the correct answer for this problem is 1. Why is it 1, Professor? Well, because all of the fluid joined back together in the condenser. This was 1 minus Y. This was Y. This is 1 minus Y. And when you add them together, you're back to 1. 100%, 100%, 100%. Makes sense? So guess what? The equation for Y for this closed feed water heater is a lot easier. It's just H7 minus H6 divided by H2 minus H8. I should say easier to rederive. All right. you can also do another one. You can take that liquid, instead of putting it through a pressure drop and feeding it back to the condenser, you could put it through a pump and just feed it back and mix it and then go in the boiler that way. You have an option. There's two options typically. You can pressurize it or drop it to a lower pressure, but you got to put it back into the system somewhere. All right, last question for today. What is true about a steam trap? So we have inlet state 1, outlet state 2. Is the pressure 1 equal to pressure 2? Is that what's true? Or is the temperature 1 equal to temperature 2? Is that true? Or the specific volume? Or the enthalpy? Or the entropy? Which is true for the steam trap? Once I click this off, then we'll shut it down for the day. But let me get everybody's answer. Is everybody's answer in? All right. All right, so the correct answer is D. Why is that the correct answer? It's a throttling valve. So please read the textbook. Please solve a lot of problems.